Hi everyone, and welcome again to this lecture. In this lecture, I want to talk about linear dependence and linear independence of vectors or vector sets. So let's go over the definition. Again, you have a vector set of vector, and I call that S in Rn, and consider the vector equation C1v1 plus C2v2 plus CKvk equals to 0. And this is sometimes just a homogeneous system. So if C1, C2 and equals to C2 equals to dot 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 CK equals to 0, or CI equals to 0 for all i's, that's has only, so if that equation or that system has only the trivial solution, we saw what the trivial solution is when all the coefficients are 0, then v1, v2 dot 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 vket are linearly independent. Or you say the set S is linearly independent set of vectors. Otherwise, when you solve this equation or this system, and at least uh, one of the C's is not equal to 0, and some Ci's are not equal to 0, then you say the set is linearly dependent, or the vectors are linearly dependent. So basically the test for linear dependence is just the homogeneous system AX equals to 0. Now let's go over some theorems. This lecture, that's what I want to do, and then some little proofs. So given V a vector space, and we only have one vector in S, which and S is in V, and that vector is not the 0 vector, is not equal to 0, then S is a linearly independent set of vector. The proof is pretty straightforward. You write the vector equation C1 V1 equals to 0. We know that V1 is not equal to 0, so the only way that can be 0 is when C1 is 0. So C1 must be 0, so it has only the trivial solution. Next theorem, given a vector space V, same way. We have a set of vector, and it does have the 0 vector in there. So that's in V. So it has the 0 vector as one of the vectors. So one of the vectors is the 0 vector that is going to be linearly dependent. Proof of that, if we write the vector equation again, or the homogeneous system, you get C1 times 0 plus C2 times V2 and so on equals to 0. If you just take that first one, C1 times 0 equals to 0, and even if C1 is not equal to 0, it's going to be 0. So if not, you're not sure if C1 will be 0 or not. So, and I put C1 can be not equal to 0. It can not have only the trivial solution. That's why it's linearly dependent. Next, if V is a vector space, so again, we know S is in V, and we have K vectors, K is greater than or equal to 2. S is linearly dependent if and only if at least one of the vectors in S can be written as a linear combination of the other vectors in S. Let's go over the proof of that. I picked vector 1 to not be equal to 0, and I showed vector 1 can be written as a linear combination of the other vectors. So let's go over that. We write the vector equation, and with this we can isolate C1 V1, which is going to give us negative C2 V2, negative C3 V3, and so on to CK Vk. If we divide everything by C, then we get those coefficients. And I did call them, just to make it easy, negative C2 over C1 as B2, negative B2 and this one as negative b3, and so on. Why did I do this? Just to write v1 as b2, v2, b3, b3, and up to bk, vk. So if we write the equation for this, or if we take everything to one side and can take that to the other side, write negative v1, makes it faster, and put it equal to 0, we do obtain that vector equation or the homogeneous system. If you look at that, the coefficient of v1 now is negative 1 and is not equal to 0. Therefore, it doesn't have the vector equation, will not have only the trivial solution. So at least one of the coefficient is non-zero. It does not have only the trivial solution. So therefore S is linearly dependent. Another theorem, again, V is a vector space and we have S. Here I put two vectors in S, and that's all, of course, in V. S is linearly dependent if and only if V1 equals to alpha times V2. Alpha is a scalar here, or V1 and V2 are scalar multiples of each other. We saw what this was, or we can see if the vectors are parallel. So the proof of that, if you take C1, the vector equation, V1, C2, V2, put it equal to 0. Then V1 can be written as alpha times V2 plus C2 times V2 equals to 0. If you factor out V2, you're left with C1 times alpha plus C2 equals to 0. For this to be 0, then you can take C1 alpha plus C2 equals to 0. And we know that C1 will be negative C2 over alpha, and C1 will not be equal to 0. So the equation does not have only the trivial solution, therefore it's linearly dependent. Next, a set of vectors again in Rn. We have k vectors. So be careful, we have k vectors and we are in Rn. Is automatically linearly dependent if k is greater than n. What do I mean by that? Let's say you are in R2 and you have three vectors, then for sure you have a set of three vectors. That set will not be linearly independent because you have more vectors than the dimension. And the proof can just write if k is greater than n, then at least we know for sure one of the vectors can be written as a linear combination of other vectors in the set. Therefore, S will be linearly dependent. An example of that I did put here. So we are in R2 and we have three vectors. And this is linearly dependent because we have three vectors in R2. The next videos, we're going to see more of examples of see if they're linearly independent or they're not. Again, just to tell you, if you have a vector, set of vector, and you want to know if that set of vector can be a basis for a vector space, the set has to have linearly independent vectors, or the set has to be linearly independent and has to span the entire vector space. I do have examples in my next videos and examples of just showing if it's linearly dependent or independent. Thank you for watching. Please again watch this video 2 or 3 times, and you can go over those proofs for sure. Try to redo it yourself, and I will see you in my next video. Have a good one, everyone.